Hello everybody. In this tutorial we shall talk about state machines in structured text. As usual, we shall explain the concept with a sample application. If you have not subscribed yet to our channel, consider subscribing to our channel. A state machine is a programming architecture that allows the dynamic flow to states depending on values from previous states or inputs. State machine are used in application where indistinguishable states exist. Each state can lead to one or multiple states and can also end the process flow, or come back to initial state. The biggest question is how we find the states in our process, or in that process that we are controlling. So we are going to identify those steps for our fictitious yard gate example. We have the sample application, which we developed for historian example. You could check the historian tutorial also. In this application actually we have data historian, PLC state machine program, and animation. In this tutorial, we shall talk about state machine only. Yard gate states, we can start that application and from there we might need to go to the initialization state. And then to the closed state. If we try to open then it can go to that opening state. And from the opening state, it can go to the open state. If there is no obstacle in front of the gate, it can go smoothly. Or it can go to that block state if there is an obstacle in front of the gate, and finally it goes to the open state if the obstacle is removed. From an open state, it can go to that closing state, and from a closing state, it can go to block the state if there is an obstacle. It can go to that closed state if the obstacle is removed as in this diagram. Also if we know the process well enough, then we can know the states already. For example, for our yard gate, here we have an open state. And if I press close and then it will go to the closed state. So here it is going to be closed state. So now it is closed. And if we open it, and then it will go to opening state. If we introduce an obstacle and it goes to a blocked state and if we remove that blockage it continues the movement in the same direction. And now if we can obviously introduce the obstacle again and if we remove it, then it is continuing the opening. So again it goes to that open state now. We can start thinking about how we are going to implement this. So we are going to show the state machine implementation by using structured text. By the way, if you have not seen that, this is described in this HMI site. And here is this address so please take a look. We can describe the state by an enum, for example. And here is some enum data type that we have identified. Like initialize, closed, opening, opened, closing and blocked etc. Some people actually use number to describe states. But I prefer to use enums data so that more clear than numbers. Let me create a skeleton program by using these enums. So I have already created a PLC program using Visual Studio. Here is the application and now I am going to add those enums here. Then, we can implement the gate control as function block. So let's introduce a function block to our project. Add then POU. Rename the function block FN main yard gate. We shall use the enums to describe each state of our yard gate. We shall have a variable state which will take a value of the enums. More information and reference can be found at HMI. We introduce these variables, this state variable and last movement and the state in it. So that means like every time, the state will be expressed by this enum variable and we are initializing it to yard on init. Then the last movement will remember that last movement in which direction it was moving. We need this because of the obstacle. When we have that obstacle, Then we know which direction it should go after obstacle removal. Whenever an obstacle is introduced, then we assign the direction to the last movement. When we use the gate, it changes its state. When it is going to a new state, then we change the state variable to the new one. In the next PLC cycle, we'll use the new state. We might need to do single-time initialization to that state. We shall tackle that by state init variable. After doing the initialization, we shall change it to true, so in the next cycle it will not execute the initialization part anymore. So state init is a helper variable. Now we can use a case statement in structured text like switch in other programming. And then we copy and paste some skeleton code. By copying from the Hemelic site. So we have skeleton code, and of course we declare a variable of type of our function block in the main program. Then we call this function block. If all okay, then we should be able to build it. Here we have implementation as we have introduced in these states. So basically, when this state case is executed, then after initialization, we set it to true. So in each case, we are checking the state init and setting it to true. And then this statement will be executed. And now, in this case, we don't have any way to go to that next state. So for example, if we execute this program, it will stay in the same state. And we can try to test it. And as you see, this state init is true. And every time the value of state is yard on init. So if you put a breakpoint here, then it will come here all the time. Then it will come again and again to that same point. But of course, this is not our intention because we want to go to that next state. So how do we go to that next state for initialization purposes? Before continuing, we can introduce some little more variables. For example, some variables we need for the HMI. But these are not necessary for our PLC program. These variables are not needed for state machine design, but we need these variables for HMI. For example, in each state, we have a description of each case which can be displayed in the HMI. For example, gate status express the status of the gate. From PLC, it will be shown here. And then there are some timing information. We are displaying on HMI that will be calculated when moving. The calculated remaining time will be displayed on HMI. In the HMI, we have some other variables are displayed. Time-related variables, and those are here. We need time for initialization that we call init time. We are assuming that it is 5 seconds, because the design is totally simulated, and then we have a timer for that. We have also opening time and closing time. And finally, we have some inputs and output for running the system. For example, we are displaying this output when the door is moving, so we are putting this output active. And when it is closing, we are putting the close output active. And when the gate is opening, then we are putting this open output active. And when the door is open, then we put the output switch active. We are changing the color of the input switch. So based on these variables, we can check the state of our state machine. So let's continue the implementation. We update the state description variable to gate uninitialized. And we set state init to true because we want to execute initialized part single time. If state is not changed, it will execute same case again and again, but the single part will be executed only once. Now we can set the new state to yard init. Also, we set state init to false, so the next state will be executed a single time. Now we directly telling that after yard on init go to yard init in next PLC cycle. Let's test the program by executing it in TwinCAT environment by login. Now we see that the value of state variable is yard init. Now we put a breakpoint in yard init. Execution stops at the breakpoint. It will execute the same case again and again. Since we have the state init variable true, it will execute non-single part again and again because each PLC cycle we have same state. We can initialize some code and go to next state. Initialization code depends on the process what we are controlling. We are going to initialization code in this case to do some simple conversion tasks. We convert the opening and closing time to milliseconds and assign to two variables for HMI. Open time to open time milliseconds. We set state init to false, so initializing part will execute single time. We have a single execution part and then multiple time execution parts. Multiple execution parts will be executed again and again until we set the state to something else. And then we have the timer variable of TON type. And we set that timer to false, because first time it will execute this part. After the first time it will execute this code which are here. Here there is nothing now, so it will not execute anything. So we put some code here. We have inserted some timer related code. In this state, first time it executes single execution code. We have put the state timer to true and it will use the init time value of 5 seconds. After 5 seconds, state timer will expired. When the timer has expired, then we assign the new state to the state variable, in this case it is yard closed. We set the state init to false. In the next PLC cycle, the state will be yard closed and state init false. It will execute the single execution part of the case yard closed. It will wait here, because we don't have any code for execution in rest of the case. By the way, you can check timer-related video done previously. Because in this tutorial, we use timer to simulate. Let's copy-paste some code for the yard closed case. We initialize the state description, input, output variables, and timer to false. We need an output variable of this function block, that is closed of type Boolean. We set the value of is closed to true because we are in closed state. We are resetting the opening and closing time to a default value. Because every time when the gate opens or closes, then if there is an obstacle, we need to recalculate the opening or closing time. So we set to default times in the open state and closed state just in case. If there were no obstacles, then we don't need this time resetting. Let's put some code what can happen when the gate is closed, only it can go to opening state. So we give an option for opening the gate. If the Boolean type variable gateOpen command is true, we can set it from PLC program or by HMI. If we set the gateOpen command to true, then it will go to that yard opening state in the next PLC cycle. Also, we set the state init to false, so the single execution part will be executed for a single time. Rest of the code will be more or less similar, so I fill other cases offline and coming back. Okay, now I have implemented rest of the code. And now if we somehow manage to set the gateOpen command to true, then the door will go to opening state. Or if we set the gateClose command to true, it will go to closing state. So depending on the value of state variable and the command set, it will react to do accordingly. So let's compile and log into our application. The gate is in yard closed state. We set the gateOpen command to true. And as we see, the timer has been fired and the timer's output Q will be true after 10 seconds. It will go to yard open state provided no obstacle. We can manage these open and close case by using an action. So let's insert an action to our yard gate function block. We give the name process yard gate and we need to put some code there. Again, we copy-paste the action code from HMI site. So here we are telling like if the gate is closed and then the gate open command to true. Then go to state yard opening and of course, again we are setting yard opening to false. If the yard gate is opened and then the gate close command is true, then we set the state to yard closing. So that is one way to implement or handle the command. Anyway, we can handle this type of case in different way and choose your way which one you see better. We can use many if else to do the same what we are doing in the action. Action is a much more elegant way to write code in this type of case. So we call the action at the beginning of the function block, so it will be called each time. That program will be called from the main, then it will call the function block, then it will check the action. Here it will check if there is any command is set. It will go through all the cases one by one to find the matching case. Every time it will not execute every case, it depends on that state variable. So this is basically the implementation of our state machine for our yard gate. Let me compile the code, start and log into the program. I can write different values to different variables to test the program. Now I set the gate open command to true to open the gate. And if I set it to true, then it is opening. And we can set the moving object detected to true. So it is now blocked. Now if I remove that obstacle and it is going to continue the opening. Finally it is in the yard open state. Since it is in yard open state, then I can set the get close command to true to close the gate. It will go to the yard closing state. While the gate is closing, then I can introduce the obstacle to block the gate. Again I set the moving object detected to false, so it will continue the closing. So thank you for watching this video. If you like this video, please give us a thumbs up. Also, consider subscribing to our channel. You can download the source code from the HMI site. The code should be ready to build and test in your TwinCAT environment. We have historian and animation implementation in the same package, so it is complete application. You can find also a text version of this tutorial on the HMI page. There are many HMI and automation related articles there. You could take a look at those also. Thank you very much for watching this. Please don't forget to share it to your network. Have a nice time.